The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Right, so our third presentation is going to be given by Professor Amit Varma from Purdue University. He's going to be talking about steel plate composite walls for safety-related nuclear facilities designed for in-plane and out-of-plane demands.
Thank you very much, Gustavo, and a very good afternoon to you all. My name is Amit Varma, and I'm going to talk a little bit about SC walls designed for in-plane and out-of-plane demands. I want to point out that this is a very lengthy and very detailed topic. As you saw in the question and answer session on the presentation before, that was done by my student Kadir, who was not really talking about the design code for SC walls, but he was talking about a snippet of information related to how their out-of-plane behavior is. There is a significant interest in the behavior analysis and design of these steel plate composite walls for the third generation of safety-related nuclear facilities. After my presentation, you're going to see a very nice presentation that will be made by Keith Kugler of Westinghouse, talking about AP1000, which uses these SC walls both for the containment internal structures as well as the shield building on the outside. These SC walls are also being used for the USA PWR nuclear power plant application that is under review at the NRC. These SC walls are very important. They have gained quite a bit of prominence. You saw the first presentation at the beginning of the day that was made by Dr. Herman Graves. The title of his presentation was Why Modular Composite, and he talked very nicely about the details of efficiency related to construction and the economy that it brings in terms of plant design. There are also some feasibility studies that have been conducted on looking on this type of system for use as a containment structure. That's work that recently started in Japan. Now, the design of conventional reinforced concrete walls for nuclear facilities is governed by the American Concrete Institute Code 349. This session is co-sponsored by 349 and by 355. 355 is the Composite Committee, of which I'm a member, and 349 is, of course, the Nuclear Committee, of which also I'm a member. But there is no such code for the design of SC walls for safety-related nuclear facilities yet in the United States. And a code of this type of magnitude will be quite expansive in its scope, as you can imagine. And we're not talking about the entire code and its details, its detailing requirements, and how do you get good ductile response. That's not what we're going to be talking about today. Although in different presentations throughout the day, you've seen some important topics from that code. One of my students, Kai Zhang, talked about the requirements for local buckling, the requirements for achieving adequate composite action. We have specific requirements for achieving structural integrity, for achieving ductile behavior of the type that was being referenced just in the question and answer session before. The American Institute of Steel Construction, which here is AISC. I'm giving a talk at ACI. I feel a little bit funny talking about AISC. But AISC has formed a subcommittee to develop an appendix to AISC N690, this focusing on SC walls. The chairman of that committee is sitting in the audience, Dr. Malushte, who was a co-author on this presentation as well. This appendix is in development, and this presentation includes just a snippet of some of the design specifications and associated commentary for SC walls. When I'm faced with a 15-minute presentation, as you can imagine, I'm not going to give you some profound knowledge associated with the behavior analysis or the design of SC walls. But I am going to touch upon some of the salient features. I'm going to show you one of the important aspects that we are talking about as far as this code for SC walls is concerned, the design provision is concerned. What I'm going to talk about is a very simple mechanics-based model to investigate the in-plane behavior of SC walls. Now, I'm not going to get into the details of the formulation. That would itself take a 15-minute presentation. But I'm going to show you how that model, that simple mechanics-based model, was verified using experimental results that exist from Japan and some experimental results that we generated in the US. And also, I'll develop some detailed nonlinear finite element models. So, at some point in this presentation, there'll be two competing models that will be existing. One will be a simple mechanics-based model, and the other will be a more detailed finite element models. Then I'll use both of them to develop what I will refer to as an interaction surface in principal force space. And this interaction surface, we are going to use it for design. As you know, we're looking at things that are going to be used in continuum structures, walls, and so on. So the amount of demands that each element is subjected to is about 8. You're looking at 3 in-plane forces, 3 out-of-plane moments, and 2 out-of-plane shears. This presentation will focus on the combination of the 3 in-plane forces and the 3 out-of-plane moments. The 2 out-of-plane shears Kadir has talked about, and there are more interactions, and there's a more detailed presentation that goes through, but this presentation will focus on the combination of the 3 in-plane and the 3 out-of-plane. So I'll take that model and use it to develop the surface, or what would be the design approach for the combination of in-plane and out-of-plane forces, and this design approach will then be converted into a simple element approach that can be used by engineers in design. And I do believe that Westinghouse and AP1000 have used that approach, and Keith may probably mention that in his talk when he gives it. So the mechanics-based model, like I said, I'm not going to get into the details of the formulation or anything. I'm talking a little bit about the assumptions. The SC walls are assumed to have planned dimensions of at least equal to a section thickness. Section thickness, as you know, can be of the order of 3 to 4 feet. So these are macro elements. These are big elements that are at least T by T in their scope. They are subjected to uniform membrane forces. These are only subjected to in-plane to begin with. They are subjected to the forces Sx, Sy, and Sxy, which produces some membrane deformations, epsilon x, epsilon y, and gamma xy. And we are assuming that the steel plates and the concrete infill have compatible strains. This is an engineering approximation, and an earlier talk by one of my students talked in detail about what is the level of partial composite action that you can truly expect to get from these type of systems when you are designing them appropriately for the S over TP ratios, and what's the impact of that. Now this is the final free body diagram associated with that simple mechanics-based model. What it does is it takes that composite sandwich system, breaks it out into the top steel plate, the bottom steel plate, and the orthotropic cracked concrete in between. Without boring you with the details of the mechanics-based model, you can set up the force equilibrium equations, and the section average strains can be estimated using the applied forces. So we can develop a relationship between Sx, Sy, and Sxy, which is the applied in-plane forces, the overall section strains, which are sort of macro strains over this entire element, epsilon x, epsilon y, and gamma xy, with Ks, which is the stiffness matrix associated with the steel plates, and Kc, which is the stiffness matrix associated, of course, with the orthotropic cracked concrete. And of course, attached with their associated areas and so on. Now, once we've obtained that relationship between the applied forces and the strains, we can solve that equation. You can actually solve it simultaneously, and you can obtain the section average strains epsilon x, epsilon y, and gamma xy for any set of applied in-plane forces. You can use these strains to then compute the stresses in the concrete portion, in the cracked orthotropic concrete portion, and you can also use them to obtain the stresses in the steel. Once you obtain the stresses in the steel, you can transform them into principal stresses, SP1 and SP2, and you can use the von Mises yield criterion to determine when steel plate yielding would occur. Now, as most of these walls are extremely thick, you're looking at thicknesses that are going to be definitely more than 24 inches, and steel plates that are going to be of the order of about half an inch. Steel plate yielding is the governing failure mode in most of these evaluations. But we'll talk a little bit more about what happens when you have more compression and so on. Now, in all of these formulations, we assume the concrete behavior to be linear elastic. Of course, it was orthotropic cracked, and we had reduced the stiffness to account for the cracking behavior and so on. But it's our responsibility at this point to make sure that the calculated principal stresses have not gone into the inelastic range. In this case, what we're talking about is at least they are going to be numerically less than 60 or 70% of the F prime C, and they turn out to be actually quite lower than that because the concrete is so much more than the steel plate in the system. So we took this simple mechanics-based model and used it to predict the in-plane shear behavior of SC composite walls that were tested in Japan and some in-plane shear tests that we had conducted at Purdue. Now, of course, the experiments and their comparisons with the models itself is a very long presentation, so all I'm doing is providing you with a reference. We talked about this in the recent SMERT conference that was held in 2011. I invite you to take a look at that paper. But in the bottom line, what we're showing here is a comparison between the values calculated using the mechanics-based model for the cracking threshold, and also the values calculated using the mechanics-based model for the yielding that occurs in the in-plane steel walls. And this is a different way to plot the comparison. This is the line corresponding to 1, and when numbers are above it, essentially means that the experimental strengths were a little bit higher than what we had predicted. I also want to draw your attention that most of these specimens were subjected to axial compression plus in-plane shear, not just pure in-plane shear, but they were subjected to combinations of membrane forces SX and SXY, so they were actually subjected to multi-directional loading that we were doing the comparisons. But that's talked about more in the paper that I have related to the comparisons. Now the mechanics-based model is very good. It's intuitive. It helps us understand the behavior, but it has lots of limitations. And we needed to address the limitations. So we have different levels of modeling. You saw some of the modeling that Kadir presented where he is modeling each individual stud and tie bar and the fracture and the concrete. But in this case, we wanted to build something a little more simpler. So what we built is a layered composite shell element, which has existed in the finite element space for a long time. We use just the layered composite shell element in Abacus that has several integration points associated with each of the steel layers, each of the concrete layers. It manages to develop composite action. And of course, you can use material inelasticity. So you can model the inelasticity of steel using multi-axial plasticity, kinematic hardening. And you can also model the inelastic compression behavior of the concrete, which we were not able to do in the mechanics-based model. But you can also model the fracture behavior, the tension, the cracking behavior, the smeared cracking behavior, the tension stiffening of the concrete, and the softening model associated with that in a lot of detail, including the shear retention behavior of the concrete. And I won't bore you with the details of the finite element model that's included in the paper, but what we are showing you here is a comparison of a simple, what is essentially a shell element model of an in-plane shear experiment that was conducted by Ozaki in Japan. And what you're looking at is some very simple shell elements that have been used to model this. Since it's subjected to pure in-plane shear, I don't even need a mesh that's that small. We can even use a coarser mesh than that. What you're looking at here is the yielding in the steel plates. You're seeing the concrete layers in that shell element. You're seeing the formation of the compression struts along that 45-degree line, just the way the mechanics-based model would indicate. But here you're looking at the comparison, or actually the prediction of the in-plane shear force versus shear strain. What you're looking at is a trilinear plot, which we talk about in detail as the in-plane shear behavior. That's the cracking threshold that we were talking about. That's where you get steel plate yielding. And here you're looking at the von Mises stress in the steel plate as it increased, reached the yielding limit, and sort of plateaued out. But I'll draw your attention to the concrete compressive stresses. This is the minimum compressive stress in that compression strut, and you're seeing values that are about 2,500 psi. This was 6,000 psi concrete. So really the concrete is not challenged in the compression strut. But if you look at the tension behavior now, you're actually seeing that it picks up to F prime T and then drops it off according to the post-cracking behavior that we had defined for the model. Now, of course, we couldn't do something that sophisticated with the mechanics-based model, but we, of course, found a way to use the layered composite shell element, which already exists in Abacus and can be used with some very complex material models. The nonlinear finite element, this approach, the finite element modeling approach, was further verified. And then it was used to predict the behavior of all the specimens that were tested by Ozaki, the entire set of 13 specimens, which included effects of axial compression. We also used it to predict the behavior of specimens subjected to accident thermal plus in-plane shear, and so on. Once the model was completely verified, it was used to predict the complete in-plane behavior of the SC wall panels, subjected to combinations of SX, SY, and SXY. Now the focus was on the entire gamut of behavior, both axial tension plus in-plane shear and axial compression plus in-plane shear. After we got the results from those simulations, we looked at them and we tried to make sense of the numbers. But we found that there was a better way to represent the results. We took the results from those simulations and used them to compute the associated section principal forces, SP1 and SP2. And we plotted them, and we found an interaction surface that looked like this. The blue line is the interaction surface that was developed from these finite element simulations. That was an interesting surface. In this quadrant, it looks like the von Mises ellipse. In this quadrant, it looks like the behavior of concrete subjected to biaxial compression. And in between, you're getting that composite behavior that connects the concrete ellipse to the steel ellipse occurring in the biaxial tension response. That's because I'm looking at it in principal force space. And it made sense to us as to what was really going on. So we took this is the prediction from the detailed finite element model. Of course, this model does not account for local buckling and so on. So we took our mechanics-based model, which was simpler, something that you could write a computer program about. A short MathCAD program would do it. And we used a mechanics-based model to generate the same surface. And it's shown as the surface with the red triangles. Now the mechanics-based model is far more conservative because it doesn't allow the concrete to develop any inelasticity. What we found was that there was 4 different regions that we needed to be careful about. Region number 1 is when the section is subjected to biaxial tension in principal force space. So SP1 and SP2 are both tension. Then zone 2, which is defined by this 45-degree line, it's really this rectangle that's shown here, is when the section is subjected to axial tension plus in-plane shear. Zone 3 is when that same section is subjected to axial compression plus in-plane shear, and zone 4 is when it is subjected to biaxial compression. This really made a lot of sense to us as to what was going on with the behavior of this SC wall module subjected to SX, SY, and SXY. In fact, we realized that this anchor point was very close to ASFY, which makes sense. That's uniaxial tension strength. This point is also ASFY, that makes sense. And this is just a zone of biaxial tension. We also found that the in-plane shear strength controlled this point, and we could approximate it with just a straight line connecting the 2 dotted points. And then this point corresponded to the uniaxial compression strength, which was ASFY plus 0.85 F prime CAC. So the finite element helped me generate the blue surface. The mechanics-based model helped me generate the dotted line with the triangles. But looking at all of this behavior, it became clear that we could come up with a simple interaction surface that could be used for design. And an interaction surface that's far more intuitive because it differentiates the behavior in different zones 1, 2, 3, and 4 that we can use to perform the design. So we were excited about this. So we said, well, we got to add the out-of-plane moments now that we've come this far. We've understood what in-plane shear does, so we decided to add the bending moments to it, MX, MY, and MXY. So we used the nonlinear finite element modeling approach first, and then we also modified the mechanics-based model to include several layers through the composite section and 3 more deformations. Now, besides having epsilon x, epsilon y, and gamma xy, we also added phi x, phi y, and phi xy, so that we would have the complete section response associated with SXSY, SXY, and MXMY and MXY. What we found was that the finite element model and the mechanics-based model both compared reasonably well with each other. And we also found that the behavior or the failure limit state was mostly governed by the von Mises yielding of the steel plates for reasons I've explained earlier. In this slide, what I'm showing you is a simple comparison between 2 important parameters. You've got in-plane shear on the x-axis, and you've got out-of-plane bending moment on the y-axis. The solid line is the results that we get from the mechanics-based model. The red dots are the results we get from a very detailed finite element analysis, and the blue dots are the results that we obtain using the design approach. Well, which design approach is this? I'm going to talk about that very quickly here. Both the results from the finite element models and the mechanics-based models indicated that we could develop a very simple design approach for evaluating SC wall sections. The design approach is as follows. You take the SC composite section and you divide it into 2 notional halves, a top half and a bottom half, through the cross-section. Each of those is subjected primarily to membrane forces SX prime, SY prime, and S prime XY. Where do you get these SX primes and SY primes? Well, they're calculated using the in-plane forces, SX, SY, and SXY, and the out-of-plane moment demands using an assumed arm length. So you can take mx and divide it by 0.9t, and you'll have a force couple that will add to the top half and will be a compression force for the bottom half. So you split up mx, my, and mxy, and sx, sy, and sxy into 2 notional halves, one on top and one on the bottom, both subjected just to membrane forces sx prime, sy prime, and sxy prime. And these arm lengths, we calibrated them using the results from the finite element analysis. Now these membrane forces can then be used to compute the principal membrane forces SP1 and SP2 for each of the 2 notional halves, and they can be plotted on the same interaction surface. This interaction surface is the one that I showed you earlier. It is just obtained by connecting all these points with straight line segments. Once again, it's back to the same 4 zones, 1, 2, 3, and 4. A zone of biaxial tension in principal space, a zone of tension plus in-plane shear in principal space, a zone of compression plus shear in principal space, and biaxial tension. But this surface is for half of the section. The only difference here is that the anchor points are not ASFY, they are ASFY divided by 2, because we've split up the section into 2 halves. Then for each half, you can calculate SX prime, SY prime, and XY prime, and plot them on the surface. If they are inside the surface, the design is going to be okay. You're not going to have any yielding occurring. If the points lie outside the surface, then you need to evaluate as to what's going on. So this converts it into a very simple design approach that was based on both the mechanics-based model and the detailed finite element models. Of course, this presentation, like I told you, it's far more long than what I'm talking about right now. But this is the design approach that we are considering using for looking at interactions of different forces and moments in the AISC N690 draft code. And of course, it includes many more details about how to deal with interactions between interfacial shear and out-of-plane shear for tie bars, how to develop adequate composite action, and how to design for local buckling. But that's what I wanted to talk about today. And those are some of the references that we used for this talk.